Okay, welcome everyone. Some administrative stuff. I have 7 students who still need to take the exam, so that's going to happen today. So I apologize for those of you who've been waiting anxiously for your grades. Just wait till I get all the exams today, and then I will post the grades, all right? We have 4 class meetings left, right? We have today, we have Thursday, then next Tuesday, then next Thursday, and that's it. And then the following week is finals. And I'll talk about when our final is. I don't remember if it's Tuesday or Thursday, but we'll get to that later, all right? So 4 class meetings, that's it, 4 lectures left. So what we're gonna do today is word problems. And I provided a handout so that I don't have to write all the word problems on the board. It also has all the formulas we need to do these word problems, so everything is here. And then this will probably take us most of the day. And then next class, we will start doing systems of equations and matrices. And if time permits, we might get into series or sequences in series. So we'll just see how things go. So, y'all ready?
Yep.
Okay, the final stretch here. 4 classes. Let's get it. I was telling my other class, this is the time everyone wants to check out, but try and keep yourself in it here. All right, so we're going to apply what we learned about solving exponential and log equations, specifically exponential more than log. So we'll need our calculators today. And let's just get into this. So what we're going to cover are 3 basic ideas here. We're going to have exponential growth and decay models. That's the first thing. Then we have this thing called Newton's law of cooling. And then we have logistic models. So there's 3 different topics here. And so we're going to start with exponential growth and decay. So we have this thing called uninhibited growth and decay. And there is a formula that we use for this. A of t equals A naught, that's the way you say that, A naught, times, this is multiplication, e to the kt. All right, so what this is this is a model, a mathematical model for a real world situation where we have what's called uninhibited growth or decay. So one example of this would be like a bacteria. Remember when we were talking about the bacteria that kept on growing and growing and growing? So this is something that we can use to model that. So we need to define what each of the little pieces are here. This A naught, this is all on your sheet of paper, but I'm gonna put it here anyway. A naught is what we call the initial amount. So this is how much we start with, whether it be the amount of bacteria we have, or it could be, anything that grows. You could talk about populations of rabbits, whatever. This is the amount that you start with. You can also use this in finance. If you put money into the bank, this A naught would be the amount that you start with, all right? So the initial amount. And then the K here is called the growth or decay constant. Growth decay constant. And the K is really the big thing in this model. The K tells you whether or not you have something that's growing, and then that tells you how fast it's growing. Or if it's decaying, something is going away, then it tells you how fast it's going away. So this K is really what's going to determine everything for us. And it says here on your sheet that if K is positive, do y'all see that? If K is positive, you have what? Greater than 0. If that's the case, then we have growth. If the K is a negative number, you will have decay. And so the 2 pictures that go with this, I didn't put the pictures on there, but if you have K being positive, then we should expect to see something that goes like this, exponential growth. Now that's exponential. And the reason I did not put anything on this side of the graph is because T here represents what? Time, right? T is time. And so T is like the x-axis here. So it's actually time here, all right? And this is the amount that we're going to have. This is time, and this is the amount of stuff we're going to have. So time can't be negative. Normally, we don't refer to time as negative. So our graph will be exponential. A true exponential growth graph would go this way, wouldn't it? Like that. But because time isn't going to be negative, we're only going to look to the right of this point and growth like that. Or if we have decay, it's going to go the other way. It's going to go like that and decay away like that. That's what happens if k is less than 0. Okay, and like I said, time is t. Now that could be measured, time, it's usually given in the word problem. It could be seconds, it could be minutes, it could be hours, it could be days, it could be years, right? So we're just going to have to read the problem to figure out what t is. And then the last thing is this a of t, like what does this thing give us, right? If you have the amount, you have the constant, you have the time, what does that give us? A of t is the exact amount of stuff you'd have there at that exact moment in time. So A of t is the amount at time t. Okay, so check this out. What would be, if this is our generic model for all uninhibited growth? Oh, and let's talk about the word uninhibited. Uninhibited means, like, let's say that I put a bunch of rabbits on an island, okay? And I just let them reproduce. Their population is going to grow, right? In a model like this, the population would just grow and grow and grow and grow, wouldn't it? It would just keep going. But in real life, what happens? If they grow, eventually they're going to be such a big population, they're probably going to start starving, some of them, because they're going to run out of resources, right? And so this is, even though it's a good model, it's not perfect. Later today, we're going to cover logistic models, and those will cover that scenario. It will say, okay, well, yeah, you'll run out of food, and then the rabbit population will kind of plateau off. So that's coming later. Uninhibited means it's growth without any restrictions, okay? So in this model, what's nice about it is that you could verify that the initial amount, that this makes sense, because wouldn't the initial amount be what happens at time equals 0? That's how much you have at the beginning. So just what is a of 0? For that generic model, what is a of 0? If we plug in 0 into that, you get e, and I'm plugging it in for t, right? No matter what the growth constant is, no matter how much it says we started with, if I plug 0 in here, k times 0 is 0, right? And what's e to the 0? 1. So this turns out to just be 1, right? And then what's a sub 0 times 1? Just a sub 0, right? This is a naught. This is the amount that we start with. So you can see that at time 0, you have the amount you're starting at, right? And then from there, it's either going to be growth or decay. Okay, so let's get to the first example here. Now, I did not intend for you to do all your work on here. There's not enough space. So this is, you probably want to do this on separate paper. So let's do example 1. So example 1 says you have bacteria growth, right? Bacteria growth. A colony of bacteria that grows according to the law of uninhibited growth is modeled by the function. Now they give you the function. It's going to look a little different, okay? N of t equals 100 e to the 0.045 t, where n is measured in grams, t is in days. Okay, so look, let's not freak out about the notation. The generic model uses a, right? It's saying like the amount. But this is generic. It's just like I could have said f of x or f of t. This is an arbitrary variable. They chose to use n here for the amount of bacteria they have, all right? So do y'all see that this is exactly this, right? It's exactly this. Now, they've given us some information, so let's look at part A here. Part A says, determine the initial amount of bacteria. So can you tell by that formula what the initial amount is? 100, right? 100 what? Grams. 100 grams of bacteria. All we're doing there is looking at that number right there. That number is just like the A naught was over here, right? And it's in grams because they're telling us that N is measured in grams here. Good? Just give you a bunch of those, right? A final with like 50 of these, where all I ask is for the initial amount, right? Okay, part B. What is the growth rate of the bacteria? So the growth rate, well, the growth and decay constant is your growth rate, all right? And what we do is we always look at it as an absolute value. So even if it's negative, we're going to say it's, well, you'll see, but we'll say decay or growth. In this case, it's this right here, this number, but we're going to convert it to a percentage. So we're going to take 0.045. We're going to convert it to a percentage, so move decimal 2 to the right, so 4.5%, right? And we would technically want to take the absolute value, the positive of it, but here for us, we're going to put 4.5% and then we're going to put growth. Now we know it's growth because it was positive to start, right? If it was negative, we put decay. We're going over these notes right now. Okay, good. That's our growth constant. Okay, or the growth rate, 4.5%. All right, C. What is the population after 5 days? So remember, T is measured in days, right? So all we're going to do is take that formula and plug in 5 for T. That's it. So we're going to go in here, we're going to go N, and we're going to plug in 5 for T. That's 100 e to the 0.045 times 5 right there. So we're just going to replace that T with 5. I'm going to get my calculator out, and I'm going to type this all in at one time and just give you a final answer. And then I will hope that you can do that on your own as well. $125.23-ish. 125.23 what? Grams. You don't have to. This is an approximation because I did round, so this means approximately. That pretty straightforward so far? Okay, part D is going to be, I guess, the hardest part of this problem, part D. So for part D, it's saying, well, not D, D and E. So part D says, how long will it take for the population to reach 140 grams? Now that's different than what we were just asked, right? We were asked how much is there after 5 days. This is saying how long, right? How many days does it take to actually get to 140 grams? So what I'm going to do is I'm going to take my generic equation. I want to know when this is going to equal 140, right? I want to know what T I plug in here to get a 140 right here. So I'm going to write 140 equals 100 e to the 0.045 T. And see, the thing I'm solving for here is what? T. And where does T live? Up in the exponent. How do you solve for T when you have how do you solve for a variable if it's up in the exponent? We're going to need some logs, right? We're going to do something with logs to do this, right? So you just had a test, some of you have not, on this idea. So what would your first step be? There's an important step before you go to log here. Are you saying switch it to log form? Right, before though, you can't do that yet because we have something to a power, but we've got this 100 in front, right? Divide both sides by 100 first, okay? So divide both sides by 100. And then you get over here, 1.4 equals e to the 0.045t. And now you can convert that to a log. Now you can. So this would become log what base?
Wouldn't it be natural?
Well, it will be natural log. Yes, it's going to turn out to be natural log. I'm just going to write first, though, log base e, right? So I'm trying to kind of like do the loop here on this thing. So e goes here. On this side, I have to put 0.045t. And then inside the log goes to 1.4. Is that clear, everyone? We're doing the loop. Well, we're building the log from the idea of the loop. So just double checking, if I take e and I raise it to that power, it equals that. And that's what I have here, right? E to that equals that. However, this right here really means, because our base is e, this really means natural log. So this is the natural log of 1.4 equals 0.045t. Now you do natural log of 1.4 on your calculator. And I'm going to continue up here. I just erased what I need on the next problem. It's okay. Okay. So now this is 0.33647. I'll just go about 5 decimal places. Equals 0.045t. What now? Divide. Divide both sides by?
0.045.
Yeah, 0.045. I'm getting around 7.4, 7.5, somewhere around there.
If it stays, can we do like 7?
Yeah, it's not that important. 7.4, everyone's going to maybe have something a little different. I'll squiggly it again. About 7.48, but you need to say what the units are, so days. It takes about 7.48 days for us to have a population, or for our bacteria to grow to 140 grams. We good? Okay. Part D. What is the doubling time for the population? So that's really saying how long does it take for it to do what? Double. What did it start at? 100. So if you double 100, you get 200, right? So I'm basically going to do the exact same thing I just did here a second ago, except instead of 140, I'm going to put 200. That's double what I started with, right? So for part D, part E, the doubling time, 200 equals 100 e to the 0.045t. So that is double the initial amount, right? The starting amount was 100, that's double it. If it asked for the tripling time, then I would have 300, right? So it just depends on what the question states. I'm going to follow the same method. I'm going to divide both sides by 100 first. Nice numbers here, right? 2 equals e to the 0.045t. I rewrite this using the log base e. This is a 2. This side is 0.045t. I'm following the exact same format as the previous problem, right? This really means natural log of 2. Get your calculator, natural log 2. 0.693147, something like that. So 0.693147. Have I talked to y'all about this? I feel like I haven't. Sometimes you'll see that when I write decimals, I'll put a 0 in front of the decimal, and sometimes I don't. Have y'all noticed that? I don't know. So it actually doesn't matter how you do it. If you write 0.13, that's exactly the same as writing 0.13, right? So the reason why people do this is because it's very clear that there should be a decimal here. let's say that I wrote that decimal really, really light and you could barely see it. That would be weird to see 0.013, right? Like you'd be like, why'd you write 013? And then you would think, okay, well that must mean that there was a decimal there. But here, if I just like barely write the decimal and you don't make it out, you might actually think I wrote the number 13. So it's just to kind of like be sure that you're like expressing that it's a decimal, but it's not necessary, okay? So, just letting you know. Okay, so over here, do this again. See, if I just do 0.045t, that's the same exact thing. All right, do my calculation. 15.4. T is approximately 15.4 days. There we go. We're done. All right, what do you think? That pretty okay? Nothing crazy? All right, so that problem is just to kind of get you used to the idea of how this works. The problem that you're more likely going to see on your final, right, is the next one. What do you notice right away about the next one? Just right away, what's the big difference? No formula. Do you see that? There's no formula given. There is no formula given to you, which means that somehow they have provided us enough information where we are going to have to come up with a formula on our own. Right? We are going to have to generate the formula. So let's read through this. Example 2, bacterial growth. A colony of bacteria increases according to the law of uninhibited growth. So that statement right there tells you, right now, that tells you that you are using this formula for this problem. All right? Now, part A says, you know what? Now I'm reading A. They want me to use N, don't they? If N is the number of cells at time T, and time is in hours, express N as a function of T. So this is like the generic formula, right? That we use for uninhibited growth, but they're telling us they want everything to be N instead. Is that all right with you if I write it that way? They're just using N instead of A. This, again, is the generic formula that's used for all sorts of things, not just bacteria growth. It could be, compound interest, things like that. So this is our generic formula. They're saying, okay, if N is the number of cells, right? The number of cells. I'm going to put this here. N is the number of cells, right? Not grams. And T is time is measured in what here? Hours, right? It was days in the previous problem. So it says on part A, it says if N is the number of cells at time T, express N as a function of T. Express N as a function of T. Well, I know that I'm going to have an initial number of cells and then e to some growth rate times T. Okay, so we know the generic formula, but we don't know, what part do we not know? Like we can't do anything right now because we don't know what? We don't know the starting amount or the rate, right? We don't know either one of those. But, so this is the answer so far. Questions? We move on to part B. Part B. Okay, if the number of bacteria doubles in 3 hours, find the function that gives us the number of cells in this culture. So they're giving us some vital information right now. They're saying that the number of bacteria doubles in 3 hours. So what does that mean? Whatever this is, right? Whatever that is, that's the initial amount. I don't know how much that is, right? But I know that when T is 3 hours, right? When T is 3, this thing should double, right? This thing should double. So here you go. So watch what I write first and then see if it makes sense to you. I know that the amount at the end has to be double, twice as much as I started with, right? The amount that I want, it doubles. It's twice what I started with, must equal what I start with, e to the k times 3. I'm using the information that they provided me in part B, that the bacteria doubles in 3 hours. Got it? Do y'all see that when I write it this way, how many variables do you have? How many things do we not know right now? Well, I don't know, and I don't know the initial amount, right? I just still don't know the initial amount, but I do know that it doubles, right? So I don't know that, but I don't know k either, right? But if I told you to solve for k, what would your first step be? Divide both sides by and not the initial amount. And do you see it's going to go away? That's a critical step right now. Any questions on this line right here before I go to the next one? Everyone's clear on how I got that? So I'm going to divide both sides by n naught, even though I don't know what it is. It goes away here and it goes away there, and that leaves you with what? 2 equals e to the k times, I'm going to write 3k instead of k times 3. Right, 3k. That's the same thing, right? Isn't that convenient? And now I'm going to rewrite this as a log. Log base e of 2 equals 3k. So use the loop to verify that we rewrote that correctly. And then that becomes natural log 2 equals 3k. And then I'm going to do natural log of 2 on my calculator and then divide that by 3. So we already did that earlier. Let me just do it all together. I get about 0.2310, I'll go one more decimal, 5 is k. I'm going to say it's equal to k. I'm going to use that. So I did natural log of 2 on my calculator, then I divided both sides by 3, and you get what k is. Is that clear?
That's the growth.
This is our growth rate, right? This is our growth rate. So now what they said is if this bacteria doubles in 3 hours, find the what?
Growth.
Find the function, right? The function. Remember, we knew in part A this was the function, right? This was the function, but we didn't know what the starting amount was, did we? And we didn't know what k was, but now we know what k is. So I'm going to go to answer this question, all right? To answer this question, part B, my final answer is this. The formula we're going to use is this. That's my answer to part B. So look at, in part A, we knew generically what the function must look like, but we didn't know what k is, we didn't know what the initial amount was. After they give us some information in part B, I was able to at least figure out what the k is, right? I don't know what the starting amount is, but I know what k is. All right, good? Let's see part C. How long will it take for the size of the colony to triple? How long will it take for the size of the colony to triple is part C.
So we do the same thing.
We're going to do the same thing, right? So what do I put? I'm going to use that generic formula right there. What's my left side going to be? I want this colony to what? Triple? So 3 times the initial amount, which I still don't know what it is, right? Right? Don't we still not know what the initial amount was? Right? But we actually don't even need to know what the initial amount was. We can still figure out how long it's going to take to triple. Okay, so there, and then e to the 0.23105t. And now follow the same procedure, divide both sides by n naught. N naught goes away. You get 3 equals e to the 23105 t. And now we've been playing this game a few times now, right? We're just going to rewrite this as a log. And is it okay with you if I just go straight to the natural log now instead of having to write log base e? So this is going to be natural log 3 equals 0.23105t. And then I get on my calculator, I do natural log of 3, and then divide it by that number that I just got. What are y'all getting?
4.75 hours.
About 4.75. So about 4.75 is approximately what t is, and t was measured in hours, right? We need to state that. If you don't put the unit, it's not correct because I don't know what you mean. 4.75 minutes, hours, days, years, right? Okay. So they kind of, on part D, they kind of ruined it for us because they told us exactly what they meant there in parentheses. They said, how long will it take for the population to double a second time? So it doubles, right? How long did it take to double? To double. They told us in part B.
Oh.
3 hours, right, to double. They're saying in part D, forget what we did in part C, they're saying part D, how long would it take to double a second time?
6.
So it would be, so it seems like maybe 6 hours, right? Is it? What do you think? Let's see, we have to figure it out. This is exponential growth. It's not linear growth. So if it took 3 hours to double, if it doubles again and takes 3 hours, that's not exponential growth. That's linear. It's doing the same thing every 3 hours. So it should take shorter. Let's see. All right.
Because if it was 2n.
If it was,
2n not.
oh, I want to leave this formula here. This is our master formula, right? So I want to know how long it takes to double a second time, which means to quadruple, to be 4 times what it started, right? 4 times. So for part D here, for part D, we're going to say 4n naught equals n naught e to the 0.23105t. And then we're just going to play that same game, right? Divide by n naught. You'll get a 4 on the left-hand side, right? Four equals e to the 0.23105t. Change this to a natural log.